In several videos on our channel, we have touched on the topic of neutrinos, tiny elementary particles that are byproducts of many nuclear reactions. I've been planning for quite some time to make a dedicated video specifically about these particles, which are rightly considered some of the most mysterious in all of particle physics. So, a journey into the world of neutrinos is a journey to the very forefront of physics in general and particle physics in particular. Unfortunately, fully explaining the topic of neutrinos and the mysteries they have posed to scientists for almost 100 years is quite challenging. Particle physics in general, and neutrino physics in particular, consists almost entirely of very complex mathematics, which expresses the premises, arguments, and conclusions of modern theories on the subject. Without a fairly deep understanding of several quite specialized branches of mathematics, a full discussion of neutrinos is impossible. Therefore, our excursion into the world of neutrino physics will necessarily be somewhat superficial. However, I hope that even this will be enough for my dear viewers to get some idea of what neutrinos are, what mysteries they pose to physicists, and how these mysteries are being solved. Neutrinos belong to the family of leptons, which are particles that do not participate in the so-called strong interaction that holds protons and neutrons together in atomic nuclei. As a result, leptons generally do not form complex structures and exist mostly independently. The most well-known lepton is the electron, which also has two older brothers, the muon and the tau lepton. They are similar to each other, having the same negative electric charge, but differ in mass. The muon is about 200 times heavier than the electron, and the tau lepton is about 3,500 times more massive than the electron. Moreover, unlike the stable electron, the muon and tau lepton have short lifetimes. The muon decays on average after 2 microseconds, and the tau lepton even faster, after about 30 picoseconds. The electron, muon, and tau lepton are also known as charged leptons, and it turns out that the birth or disappearance of charged leptons in various elementary particle transformations is accompanied by the birth of neutral leptons known as neutrinos. The most commonly encountered example of reactions that produce neutrinos is beta decay, specifically beta-minus decay, during which a neutron in certain unstable nuclei transforms into a proton, simultaneously producing an electron and a neutrino. Beta decay occurs in a large number of radioactive elements, making this type of radioactive decay one we encounter most frequently in everyday life. For instance, the radioactive isotope potassium-40 undergoes beta decay to become calcium-40, releasing an electron and a neutrino. About 0.01% of natural potassium atoms are potassium-40, so beta decay with neutrino production occurs to some extent in all potassium-containing substances. Bananas, for example, are rich in potassium, making an ordinary banana a natural source of neutrinos. However, there's no need for concern. Neutrinos have almost no impact on the human body, or on anything else for that matter. Being leptons, they do not participate in the strong nuclear interaction, and their lack of electric charge means they also ignore electromagnetic interaction, participating only in the so-called weak interaction, which is weak by name and nature. As a result, neutrinos hardly interact with matter at all. To intercept half the flow of neutrinos from a given source, you would need a lead shield as thick as the orbit of Saturn. Therefore, neutrinos pass almost unimpeded through massive objects like the Earth or even the Sun, let alone something like the human body. Trillions of neutrinos pass through us every second without any noticeable effect. For scientists, this property of neutrinos poses a significant problem, as detecting such elusive particles to study their properties is extremely difficult. Neutrino detectors are enormous containers filled with various substances, surrounded by sensitive detectors in the hope that some of the billions of neutrinos passing through the detector volume each second will interact with the substance, and that the results of this interaction can be recorded. Even in large volumes of detectors, such interactions are very rare, so neutrino experiments often last for years before accumulating enough data for meaningful analysis. Aside from beta-minus decay reactions like the one potassium-40 in bananas undergoes, there are many other reactions that produce neutrinos. For example, there is beta-plus decay, in which a proton in the atomic nucleus transforms into a neutron, releasing a positron, the electron's antiparticle, and again, a neutrino. There is also electron capture, during which a proton in the nucleus absorbs an electron, turning into a neutron and emitting a neutrino. Neutrinos are also emitted in reactions involving other charged leptons. For instance, charged pions, which I will sometimes refer to as pi mesons, decay in about 26 billionths of a second into a negatively charged muon and a neutrino, in the case of negatively charged pions, or a positively charged antimuon and a neutrino. Moreover, the muons and antimuons produced by such decays will themselves decay in about 2 millionths of a second into, respectively, an electron or positron, also producing neutrinos, specifically 2 neutrinos, but more on that later. Right from the beginning of neutrino studies, physicists faced a question. Are the neutrinos produced in different particle transformations, the same particle, or are they different? Part of the answer to this question was obtained through experiments initially aimed at determining whether the theoretically predicted neutrinos existed in practice. Several groups worked almost simultaneously on the task of detecting neutrinos, among which the experiments by Raymond Davis and the experiment by Frederick Rines and Clyde Cowan are of particular interest. Davis aimed to detect neutrinos using a method proposed by the Soviet physicist of Italian origin, Bruno Pontecorvo. The idea was as follows. The radioactive isotope argon-37 undergoes the previously mentioned electron capture, during which a proton turns into a neutron, and argon-37 becomes chlorine-37 while emitting a neutrino. Pontecorvo suggested that the reverse process might be possible. If a neutrino hits the nucleus of a chlorine-37 atom, one of the neutrons in the nucleus will turn into a proton, emitting an electron. Thus, if we place a large container of chlorine or its compounds in a neutrino stream, we can expect that over time, some chlorine will turn into argon. Since such a transformation is possible only under the influence of neutrinos, detecting the production of argon would confirm the existence of neutrinos. Davis decided to try this by placing a 3,800-liter and later an 11,400-liter tank of carbon tetrachloride near a working nuclear reactor, which was expected to produce a powerful neutrino flux, and waited to see if argon would form in the tank. Rines and Cowan took a different approach. They decided to search for events related to the interaction of neutrinos, also produced by the nuclear reactor, with another component of the nucleus, the proton. Upon absorbing a neutrino, the proton should turn into a neutron, emitting a positron. Rines and Cowan used ordinary water with dissolved cadmium chloride as their target. Each water molecule contains 2 hydrogen atoms, whose nuclei are essentially single protons. Thus, when a neutrino hits the nucleus of a hydrogen atom, the atom disintegrates, emitting a neutron and a positron. The positron quickly annihilates, with one of the electrons in the water solution of cadmium chloride, producing 2 gamma quanta of a specific energy, essentially a flash of electromagnetic radiation that can be detected. The neutron, in turn, is absorbed by a cadmium-108 atom, which turns into cadmium-109, emitting a gamma quantum, another flash. Therefore, each interaction of a neutrino with a proton should produce a characteristic double flash that can be detected and reliably distinguished from other signals. Rines and Cowan aim to register these double flashes as proof of neutrino existence. I must emphasize, both methods should yield results if neutrinos exist and fail if neutrinos do not exist. However, something strange happened. Rines and Cowan's setup worked, confirming the existence of neutrinos, while Davis's setup did not. This raises the question, why did this happen? The answer was found fairly quickly. The 2 setups were designed to detect different types of neutrinos. Davis's experiment required neutrinos to transform chlorine into argon, while Rines and Cowan's setup was designed to detect antineutrinos. To explain how this works, it's useful to introduce the concept of lepton number. Leptons, both charged and neutral, have a lepton number of +1, while antileptons, like positrons, antimuons, and antineutrinos, have a lepton number of -1. It turns out that in weak decays, including beta decay and other reactions, the lepton number must remain constant. Take the most common beta- decay reaction, where a neutron transforms into a proton. The initial lepton number of this reaction is 0. As a result of the reaction, an electron with a lepton number of +1 is produced. To maintain the overall lepton number, an antineutrino with a lepton number of -1 must also be produced. This ensures the lepton number conservation rule. +1 - 1 equals 0. Everything is in order. In beta plus decay, a positron, an anti-electron with a lepton number of -1, is emitted, so a neutrino with a lepton number of +1 must be produced alongside it. Let's look at Davis's and Rhine's and Cowan's experiments from this perspective. In Davis's experiment, an electron is produced, resulting in a final lepton number of +1. This means that the initial lepton number must also be +1, indicating that neutrinos with a lepton number of +1 are needed to initiate this reaction. Antineutrinos with a lepton number of -1 cannot trigger this reaction due to the lepton number conservation rule. On the other hand, in Rhine's and Cowan's experiment, a positron is produced, resulting in a final lepton number of -1. Therefore, antineutrinos are required to initiate this reaction. Nuclear reactors, which both groups used in their experiments, emit a stream of antineutrinos that can trigger the reaction Rhine's and Cowan were looking for, but not the reaction in Davis's experiment. This is exactly what happened. Rhine's and Cowan's setup detected neutrinos, while Davis's did not. This is a classic case where a negative experimental result is still a result. Davis's inability to detect neutrinos helped confirm that neutrinos and antineutrinos are distinct particles. This hypothesis was further confirmed when Davis repeated his experiment using ordinary neutrinos from another source, and it worked. The second question is whether the neutrinos accompanying reactions with different charged leptons, such as electrons and neutrinos, are the same particles. To test this, another experiment was conducted, similar to Rhine's and Cowan's, but with a different neutrino source. This source was a particle accelerator that sped up protons to high velocities and then bombarded a beryllium target. This bombardment produced many positive and negative pi mesons, which soon decayed, emitting negatively charged muons and, due to the lepton number conservation law, antineutrinos, as well as positively charged muons and neutrinos. The resulting neutrino stream, composed of neutrinos and antineutrinos, was directed at a substance. Neutrinos were supposed to initiate Pontecorvo's proposed reaction, turning a neutron into a proton and releasing an electron, while antineutrinos would turn a proton into a neutron and release a positron, as in Rhine's and Cowan's experiment. Previous experiments had already shown that such reactions occur. However, when physicists Lederman, Schwartz, and Steinberger conducted their experiment, they did not observe the expected production of electrons and positrons. The explanation was that neutrinos produced in reactions involving electrons are different from those produced in reactions involving muons. These particles were named electron neutrinos and muon neutrinos. Additionally, we now know of a third lepton pair, or generation, the massive tau lepton and tau neutrino. For example, the previously mentioned muon decay into an electron and several neutrinos occurs as follows. The muon decays into an intermediate particle known as a W boson. Since the lepton number decreases by 1 in this reaction, a muon neutrino must also be produced. The W boson then decays into an electron. In this reaction, the lepton number increases by 1, meaning the production of an electron must be accompanied by the appearance of an antineutrino. Specifically, an electron antineutrino. Thus, by the late 1960s, the theory of neutrinos had more or less taken shape in the form we discussed at the beginning of our video. There are 3 types, or flavors, of neutrinos, as physicists call them, and 3 corresponding antiparticles. In this first version of the neutrino theory, neutrinos were considered not only charge-free, but also massless. There were fundamental reasons to think this way, which we won't delve into here, since it would require near-lethal doses of mathematics. However, it soon became apparent that neutrinos likely do have mass. This discovery came thanks to Raymond Davis, who, as we mentioned earlier, did not give up trying to detect neutrinos using his chlorine-argon detector by the Pontecorvo method, but changed the neutrino source from a nuclear reactor to the sun. As is well known, the source of the sun's energy is thermonuclear reactions occurring in its core, and a byproduct of these reactions is a significant amount of electron neutrinos, which were supposed to trigger the chlorine-argon reaction proposed by Pontecorvo. To detect solar neutrinos, Davis built a new detector in the former Homestake gold mine in South Dakota. The detector was a steel tank with a volume of 380,000 liters, filled with 615 tons of tetrachloroethylene. This time, Davis succeeded. He detected a flux of solar electron neutrinos. However, there was an unexpected result. The detected number of neutrinos was 3 times less than expected. Here's the issue. We know quite well how much energy the sun emits, and we are confident that all this energy is produced through known thermonuclear reaction chains in its core. We know the energy output of each chain, allowing us to calculate how many such reactions occur inside the sun per unit time. On the other hand, we know how many neutrinos should be emitted during each reaction. So by multiplying the number of reactions per unit time by the neutrino yield of each reaction, we can get a fairly accurate estimate of the density of the neutrino flux emitted by the sun, including the density of the solar neutrino flux passing through the Earth. Of course, the Homestake detector and even more advanced modern neutrino detectors capture only a tiny fraction of the neutrinos passing through them. However, we can accurately calculate what fraction they capture, and knowing how many neutrinos the detector captured, we can calculate how many neutrinos actually passed through the detector. The fact that the number of neutrinos detected by Davis at Homestake was 3 times less than expected suggested that the thermonuclear reactions inside the sun were occurring 3 times less intensively than we thought, meaning the sun couldn't shine as brightly as we observe. This puzzle became known as the solar neutrino deficit problem, and it required a prompt solution. There were several ways to explain the solar neutrino deficit. The first and simplest was the assumption that Davis simply made a mistake. However, this version was rejected after other experiments confirmed the solar neutrino deficit. Later, more precise measurements showed that the neutrino deficit was somewhat less than Davis had determined. Instead of losing 2/3 of the solar electron neutrinos, only about half were missing. This did not eliminate the need to understand where they were disappearing. Our understanding of the physics of the sun could also be fundamentally wrong. For example, if thermonuclear reactions were not the only source of the sun's energy, the solar neutrino deficit could be naturally explained by less intense thermonuclear reactions in the sun's core than previously thought. However, if we accept this explanation, we simultaneously need to explain where the sun gets its additional energy. Several intriguing hypotheses were proposed. For example, one suggested that the sun might derive part of its energy from a small black hole located somewhere in its core. Although we don't think there's a black hole inside the sun today, the concept of black holes as potential alternative energy sources for at least some stars gained its own life, and we have a separate video on our channel about this topic. Moreover, something might be wrong with our estimates of the neutrino's penetrating power. If, for instance, it turned out that neutrinos are absorbed by matter more than we thought, the solar neutrino deficit could be explained by a significant portion of the neutrinos created in the sun's thermonuclear core being absorbed by the sun's material on their way to us, leaving only a fraction to reach us. However, the most intriguing explanation to scientists was the idea of neutrino oscillations proposed by Bruno Pontecorvo, according to which neutrinos initially produced in the sun's core as electron neutrinos partially transform into muon and tau neutrinos on their way to Earth, which Davis's detector and similar detectors simply cannot see. The theory of neutrino oscillations is extremely complex from a mathematical standpoint, so I won't even try to explain it thoroughly. However, I will attempt to give my viewers at least some idea of how, according to modern physics, it all works. According to Pontecorvo's theory, the electron, muon, and tau neutrinos that we detect in experiments are actually a superposition or mixture of 3 particles, which can be called neutrino 1, neutrino 2, and neutrino 3 in various proportions. The type of neutrino we detect in a given experiment, whether it's an electron, muon, or tau neutrino, depends on the degree to which each of these 3 types is present in the detected neutrino. It's important not to think that neutrinos physically contain these 3 types of neutrinos, as if they are composed of them. When we talk about superposition in particle physics, we are referring to it in a quantum mechanical sense, which can be understood by recalling that in quantum mechanics, all particles have wave-like properties. That is, any particle propagates in space in the form of the so-called de Broglie wave, a probability wave, more precisely, a probability density wave of finding the particle in a given region of space. So, according to Pontecorvo's theory, neutrino 1, neutrino 2, and neutrino 3 correspond to 3 different probability waves. And the particles we call neutrinos are the result of the interference of these 3 waves. Depending on the result of this interference, we observe either an electron, muon, or tau neutrino in the experiment. This explains how we can observe 3 different flavors of neutrinos, but it doesn't explain their oscillations. The probability waves of all 3 components of the same neutrino would propagate in space at the same speed. So if such a wave packet is formed, the same phase relationship will be maintained, and the electron neutrino would remain an electron neutrino, the muon neutrino a muon neutrino, and so on. However, if we assume that the wavelengths of the probability waves for neutrino 1, neutrino 2, and neutrino 3 are different, the situation changes. At various points in space, the phase difference of the de Broglie waves will vary, and at some points, the interference result will be such that we will interpret it as an electron neutrino, at others as a muon neutrino, and at others as a tau neutrino. Thus, as the wave packet, which we call a neutrino, propagates, the structure of this packet will change, leading to a change in the observed flavor or type of neutrino. Even if initially only electron neutrinos were formed in the sun's core, some of them will transform into muon and tau neutrinos on their way to Earth, reducing the number of electron neutrinos, which we perceive as a deficit of solar neutrinos. As we mentioned earlier, for neutrino oscillations to occur, the de Broglie waves for neutrino types 1, 2, and 3 must have different wavelengths. The de Broglie wavelength of a particle is given by this relation, where h is Planck's constant and p is the particle's momentum. For the waves of neutrino 1, neutrino 2, and neutrino 3 to propagate as a single packet, these particles must have the same speed. Therefore, their wavelengths can only be different if neutrino 1, neutrino 2, and neutrino 3 have different masses. That's why these are also called the mass states of neutrinos, denoted M1, M2, and M3, respectively. We have no means of directly measuring neutrino masses, and all experiments that identify neutrinos determine their flavor state, that is, whether they are electron, muon, or tau neutrinos. Each of these particles is a certain mixture of the mass states M1, M2, and M3. Conversely, if we could measure the mass of a neutrino, determining whether we are dealing with mass state M1, M2, and M3, we could state that this particle is partially an electron, partially a muon, and partially a tau neutrino. However, we cannot yet measure neutrino masses, and likely won't be able to anytime soon, because these masses are exceedingly small. Neutrinos are roughly 1,000,000 times lighter than electrons. This brings us to the first problem. Before the discovery of oscillations, neutrinos were considered massless. However, the fact that neutrinos undergo oscillations proves that they do have mass, even if it is very small. We might say, well, they have mass after all, contrary to what we thought. But the problem is that, according to our current understanding, neutrinos should not have mass. The prevailing theory in modern particle physics, known as the Standard Model, states that elementary particles gain mass through interaction with the so-called Higgs field, whose quantum is the famous Higgs boson. Particles that interact with this field, such as electrons, muons, or quarks, and the particles composed of them, have mass, while particles that do not interact with it, such as photons or gluons, are massless. As far as we know, neutrinos cannot interact with the Higgs field. Here, we should recall that all elementary particles, and not only elementary particles, have a characteristic called spin, the intrinsic angular momentum that a particle would possess if it were rotating in one direction or the other, although it doesn't actually rotate. Particles whose spin is such that they would rotate clockwise along their direction of motion are called right-handed, or simply right, and those that would rotate counterclockwise are called left-handed, or simply left. Now, for a particle to acquire mass via the Higgs mechanism, it must exist in both right and left forms. And most matter particles, like electrons or quarks, exist in both forms. Neutrinos are an exception. They are only left-handed, or more precisely, right-handed neutrinos have not been observed so far. Conversely, antineutrinos are right-handed and only right-handed. If neutrinos indeed exist only in the left-handed form, they cannot acquire mass through the Higgs mechanism. More precisely, they could do so only in one specific case. If they are not Dirac fermions like all other matter particles, but belong to another type of particle called Majorana fermions. The difference between Dirac and Majorana fermions is very simple. Majorana fermions have no antiparticles, or rather, they are their own antiparticles. However, experiments seem to show that neutrinos and antineutrinos are different particles, meaning that neutrinos cannot be Majorana fermions. This puts us in a bind. Neutrinos must have mass because they apparently undergo oscillations, which explain the neutrino deficit. However, they cannot have mass as Dirac fermions since they exist only in the left-handed form. They could have mass if they were Majorana fermions, but they are not Majorana fermions because they have antiparticles. In other words, we're stuck. Well, not entirely. Physicists have many ideas about how to resolve this contradiction. For instance, there are those who doubt the existence of neutrino mass and deny neutrino oscillations. There aren't many of them, but their argument has a certain logic. Yes, they say, the neutrino deficit is an observed fact, but neutrino oscillations are just one possible explanation for this phenomenon. To claim that oscillations definitely occur, we need to observe them directly, for example, by taking a beam of electron neutrinos and observing whether, after traveling some distance, some of these neutrinos turn into muon or tau neutrinos. Such experiments have been conducted, though they used muon neutrinos and checked the beam for the appearance of electron neutrinos. The results seem positive. A small number of electron neutrinos were found, but the number is literally in the single digits, giving skeptics grounds to argue that the data from these experiments is unconvincing. New experiments of this kind are being planned to provide more convincing statistics. The deadlock would also be overcome if it turns out that the previously unseen right-handed neutrinos do exist. This is possible because all current methods of neutrino detection rely on their participation in what is known as weak interaction with matter, while only left-handed neutrinos are capable of such interaction. Since neutrinos do not participate in any other detectable interactions, right-handed neutrinos, even if they exist, do not interact with anything at all, which is why we wouldn't be able to detect them even if they did exist. This is why right-handed neutrinos are also called sterile neutrinos. However, there is hope. Theory predicts that right-handed neutrinos can flip to become left-handed and vice versa with a certain probability. From the perspective of our detectors, this could appear as either the sudden appearance of some neutrinos out of nowhere or their disappearance into nowhere. Several attempts have already been made to observe this phenomenon, with controversial results. Additionally, some scientists believe that neutrinos might actually be Majorana fermions, meaning they are their own antiparticles. Yes, this contradicts Davis's experiments. But what if Davis's detectors didn't work not because they were fed neutrinos instead of antineutrinos, but for some other reason? This is possible, and more precise experiments are now being conducted to verify if neutrinos are their own antiparticles. For example, this can be determined by studying double beta decay reactions, where two neutrons in the same nucleus simultaneously turn into protons, releasing a pair of neutrinos. If neutrinos are indeed their own antiparticles, the neutrinos produced in double beta decay could annihilate each other, resulting in beta decay without any neutrino emission at all. Unfortunately, despite numerous attempts, such a neutrino-less decay has yet to be observed. However, again, we cannot rule out the possibility that we simply haven't been looking hard enough. There is also a fourth possibility. After all, we still know very little about the Higgs mechanism by which elementary particles acquire mass, and it is quite possible that neutrinos have their own version of this process. No wonder their masses are so much smaller than those of other particles. It is possible that the Higgs field has more than one carrier boson, And among these other bosons, there might be some that can interact with neutrinos. This is a great hypothesis, and the only thing left to do is to prove that these alternative Higgs bosons exist, and experimenters are working in this direction as well. With sadness, I look at the clock and realize that our discussion about neutrinos has gone on longer than I expected, and I have only covered a small portion of what I initially planned. We could talk about neutrinos for much longer, discuss modern detection methods, delve into ongoing and planned neutrino experiments, and understand what studying neutrinos can offer us and whether we can derive any practical benefits from them. In short, I would be happy to continue the topic of neutrinos, and if you found it interesting and want more, please let me know in the comments. But for now, that's all. Take care and see you next time.